So we are glad to have Huacheng from all the way across the Gulf Coast to tell us about the self-port model and data structure programs.
Thanks for the introduction and thank for everyone for coming. Today I'm going to talk about data structure programs. The data structure problem that I'm going to focus on today is called dynamic dictionary, which is probably one of the most basic data structure problems. Okay, so what is the dictionary problem? We would like to design the data structure that maintains a set of key value pairs. Let's say a set of at most n key value pairs with distinct keys from some key space with distinct keys from a key set, key space U, and also values from some value space V. And supporting insertions, deletions, and queries. Supporting the following operations, we can insert a pair. We are giving a pair a key and a value. We're going to insert this pair, or we can be given a key and delete the corresponding pair. So we are going to insert or delete pair, or the data structure needs to support queries where we are given a key and we must return whether this key is in the current set, and if so, what is its value. Return if X is in the current set, and if so, return its value. Also, it's return its value. Right. And for this talk, we should think the main parameter is the number of key value pairs as the key universe size, value universe size are polynomially bounded. So let's think for this talk, let's think that the key space is the most n because we need n distinct keys, but it's also bounded by poly n. And also the value space is also bounded by poly n. So value space can actually be small. And actually, an interesting special case of the dictionary problem is when the value space is 1, when there's no values. And in this case, we'll basically maintain a set of keys, distinct keys. We can insert a key and delete a key. And also we can query whether a key is just in the current set. It's just the membership queries. So when V is equal to 1, this is the membership. I guess this is a data structure problem that has been studied all the way back to the even 60s and 50s. And probably the most well-known and standard solution to this data structure problem is just hash tables, right? You can sample a random hash function, maybe a random pairwise independent hash function from the key space to n slots, and then store the key value pairs in the corresponding slot. And then if there are hash collisions, there are multiple different ways to resolve hash collisions. For example, we can store a linked list. And when the hash function is pairwise independent, we know in expectation there's only constant hash collisions with a given key. So we have constant query time, update time in expectation. So we know that we can use hash tables to store everything in nlogU plus log E bits of space. And also, this achieves constant time in expectation.
There's also worst case results of, at least in the static case of Feldman converse memory, right?
So in the static case, you can actually achieve constant time inverse space. Yes, correct.
But you are focusing on the dynamic.
Yes, exactly. We are focusing on dynamic case. We would like to maintain a dynamic set on the insertion deletions. So I guess there has been a lot of extensive studies after these hash tables trying to improve different parameters. For example, we can try to improve in the dynamic case this time to worst case with high probability. So it actually takes constant time in worst case except for 1 over polynomial or even 1 over exponential probability. And also there have been works that tries to improve the space even more, or try to use space in terms of the current data structures, the current data size instead of the max n. So the data structure usage will be, space usage will be proportional to the current n. But I guess in this talk, what I would like to focus on is the precise space usage of the data structure, and also the trade-off between this space usage and the time. So what I mean by the precise space usage of a data structure. Okay, so if we really think about how much space we needed to store these n p-value pairs, like let's just forget about the insertion and deletion as queries, just information theoretically how much space we need. Now we have a set of n distinct keys and also n values. So just to information theoretically optimally encode this input set, I guess we only need log u choose n plus n log v bits to encode it, right? Because we have u choose n different possible sets, we need to encode which one it is, and also for each element, we need to use log v bits to represent what it is. So regardless of the time, this is the best possible space. Information theoretic optimal space that we can use. And let me just denote it by opt. So the question I would like to focus on today is that what happens if I allow the data structure to use just a little bit more than very, very close to this information theoretic optimal space? And in this case, how does that affect the time, the running times, operational times? And it turns out that the best known solution to this data structure problem was proposed 2 years ago by Bender, Farach-Colton, Kuszmaul and Liu, that achieves very, very close to the space. Let me say, write out the exact bound. So the best known solution or upper bound gives space that is opt plus O n log n with k logs here for any parameter k and time of k. Okay, so k can be any parameter. So if I want constant time, then I can have any constant logs. And if I want, let's say, linear extra number of bits, then I can have time that is log star of n. But this trade-off all the way only goes down to linear extra bits. And this extra term here beyond the optimal space is usually called redundancy. How much extra bits?
Can you write down the names of the people who did this?
Yeah. Oh, yeah.
Amazing.
Bender, Farach-Colton. Kuszmaul. Another Kuszmaul.
So this is William Kuszmaul and John Kuszmaul?
Yes.
Okay.
2020. Okay. So this trade-off may look a bit strange at the first glance, that every time you increase the time by unit amount of time, you can add another log in the redundancy. But it turns out that this is actually optimal. And that's what I'm going to talk about today. This is a joint work with Tianxiao Li, Jinxin Liang, and Fei Zhou from last year. And actually, two of my co-authors were actually here 2 weeks ago as new admits to the Princeton CS. Okay, so we proved that a tight.
I was wondering if you proved it during the visiting days.
We published last month. Yeah, a tight lower bound, tight cell-proof lower bound. When the key universe size is not just a polynomial n, but it is also polynomially bounded away from n. And when k is at most log star of n, and word size in the cell-proof model with word size log n or log u. I guess this is one of the standard settings for word size whenever all the main parameters are polynomially bounded of each other. And in this case, we basically prove the max of the expected insertion time and the deletion time and the query time is at least k when the space is this much. Yes, for those of you who are not familiar with the cell-proof model, I will define it in a second. But let me just mention that we have this extra requirement that the key universe size is actually polynomially bounded away from n. This turns out to be necessary because in this paper they had another data structure that works when the universe size is something slightly it's something very close to n. It's something when it's n to the 1 plus, let's say, something slightly subconstant, one over log n. In that case, they can achieve constant times and also sublinear redundancy. So basically, this means that when u is just n to the 1 plus little of 1, just slightly little of 1, we cannot hope the same trade-off to hold, and we do need it to be bounded away from that. Yeah, and also so this will be the results that I will focus on today later. But let me also mention that in the same paper, we also proved a lower bound when the redundancy is less than n. So we also showed that when space is n plus r, sorry, op plus r, or r less than n, a lower bound of omega of log n over r. And also we showed that when the value space is also polynomial, then the same lower bounds, both that one and this one, holds just on the update time. So we allow the query time to be arbitrarily large. As long as there's the kernels of the query, we have the same lower bound just on the update time. When this the same lower bounds hold for that's the max of the insertion time and deletion time. So before I say what cell-proof model is, briefly, any questions about the results and settings?
Maybe one quick question.
Yeah.
Are these like close to optimal algorithms actually used in practice? Like, or is this like purely theoretical question?
Yeah. So I think okay, definitely the newer ones that they are probably not using in practice because it's very complicated. There are a lot of technical details, and I guess the leading constant in the extra term may actually be not so great, but there are also simpler ones that theoretically it's not as good as these ones, but I believe maybe some of them are actually used.
So actually just another question. So the ones you mentioned, like the ones which are not theoretically as good, but they're not hash tables, as in like there are something.
All right. Yeah. They're not exactly the hash tables like this, but actually it's overall it's still based on hash tables, but you're not storing the keys exactly as this, so that the space will be very close to all. Right? Yeah. All right. Okay. So yeah. So what is the self-pro model? Roughly speaking, this is a model where it's a generalization of it's a strengthening of the RAM model, where we only count how many times we look at the memory, and all the computation is free. I guess more precisely, what I mean is that we have a memory of some size. I guess it's will be bounded by whatever space bound we're shooting for, and this memory is partitioned into words or memory cells, such that each cell consists of W words, where W is the word size. So, sorry, W bits, where W is the word size. Okay, and then a data structure can access this memory in any way, but we only count how many times it accesses, how many cells it reads, or it writes to, and all the computation are free. So we only count the number of memory accesses. Or it's called cell probes. And computation. I guess more precisely, what I mean is that, let's say, imagine that we're running the query algorithm, which sees the query, and it based on the query decides which cell to look at, which part of the memory to look at, and based on the content there, and the query itself decide which cell to look at next, and so on. And it reads some number of memory cells, and then eventually it figures out the output of the query, and then optionally it can update some of the contents in those cells. And we only count how many times it does this cell probes, and we don't count for the decision process of deciding which cell to read next. So this is strengthening the RAM model, because you do need to take constant time whenever you read something in the memory, and a lower bound that is proved in this model also holds in general. And okay, so in this talk, just for simplicity, I will want to focus on proving this lower bound, but only for the regime where k is log star of n. Okay, so I want to focus on the case where the space is optimal plus linear, and I want to prove the lower bound lower bound on time, prove a lower bound on time that is omega of log star of n. So I would like to focus on opt plus O of n versus omega of log star of n. It turns out that the same proof strategy just generalized to the full trade-off with just slightly different setting parameters. So for the rest of the talk, instead of proving this lower bound directly in the self-pro model, I will actually do it in a slightly different model, and the proof will be like they will share the same framework, but this new model, there's just fewer details, so that I can actually present most of the details in the talk. And towards the end, if I get time, I will say what modifications that we need to do in order to adapt that proof to the self-pro model. So the model I'm going to focus on for the next, I guess, half an hour is called slot model for, I guess, for the dictionary problem. So what it does is that we assume that we have a memory of some size. And also we have n slots, which is also a part of the memory, I guess, separate from this. And we assume that the memory has size log u choose n plus, let's say, O of n bits. And what it does is that this memory part must encode the set of keys, and also must determine a mapping from the keys to these n slots. So the memory must store the set of keys and must also determine I guess when it has n keys, it's a bijection to these n slots, or an injection when we currently have fewer than n keys. Okay, so how should we think about this model? So imagine that in general, we have some data structure. Suppose the data structure has some parts of the memory that are used to store the values. So maybe these log v bits of the memory are always used to store the value of some key. And then maybe there are other log v values that bits are always used to store the value of some other key, and so on. And there are n of them. Then we can take these n log v bits out as the n slots, and the rest of the memory must store everything else and determine the mapping from these n keys to these n slots, like which keys are stored in which slots, and so on. And I guess in this sense, yeah. So for any data structure that has this form, we can fit it in the slot model. And it turns out that all the known dynamic dictionary constructions has this form. But let me just quickly mention that to determine any bijection to n slots, we don't really need this O of n extra bits. For example, we can just always maintain the mapping that maps all the keys in the lexicographic order, like the smallest key is mapped to the first slot, and the second largest key is mapped to the second slot, and so on. But that just is just very expensive to maintain. Like maybe we delete something here and insert something here, then everything in the middle needs to be shifted by one slot. So this could be very expensive to maintain. And the hope is that with these extra bits, maybe things can be cheaper. And yeah, and also in the slot model, we further assume that this entire memory is actually free to access. So we accessing the memory that's free. And we only count how many times we access slots or maybe move the values around. And only count the number of moves or accesses to the slots.
I have two questions.
Yeah.
First of all, you insist that the slots contain keys and not values there.
Oh yeah, I should actually mean that the slots contain the values. So
Slots contain the values.
the values.
Okay, very good.
Yes.
And the O of n is simply not the linear space besides log n to 0. There is no, this is not enough for a hash function. It's not enough bits to specify a hash function.
I guess it is, but you also need to resolve the hash collisions. So
even if you just want the hash function, it's a hash function, let's say from n bits to n bits.
mm-hmm.
It needs some, and this is a number of words. What is this?
Sorry, yeah, this is the bits.
Bits. All of n bits are not sufficient to specify a hash function.
Like if you want to also resolve the hash collisions.
No, even if you don't, I mean, from
don't?
n bits to n bits, if you want a hash function from n bits to n bits, you're doing like nlog n bits, right?
But actually, this is from log n bits to log n bits thing. So you have n, the universal size is n.
Yeah.
And this, you also, the target is also n. Like you can use like 2 log n bits, for example, to describe a pairwise independent hash function.
Okay.
But there will just be a lot of collisions, and you need to.
Yeah, got it. Okay,
Yeah.
very good.
Yeah.
Thanks.
Okay, I guess in this case, we only want to, I guess, count the number of access to the slots. And also because of that, this slot model is actually incomparable with the self-prone model, because on one hand, we can access this part of memory for free, but also this restricts the data structure to store those values atomically. Like it has to be stored exactly here, and in those n slots. Yeah, and also, yeah, one other thing that I like to mention is that if we, instead of n bits, if we allow to use nlog n bits, then this problem is actually trivial. This is because with nlog n bits, we can encode any mapping between the keys to these n slots. Then whenever we insert or delete something, when we insert something, we just find any empty slot, put it in there, and then update the mapping, this arbitrary mapping, which we can afford to encode. But in general, when we only have like of n bits, log n factor smaller, then we're going to show that we cannot maintain this in constant time. Yeah.
Actually, from the general problem to this problem.
Okay, so it won't be a black box reduction. Just the proof in this model is much cleaner, so that I can present it in the talk. And also, I will say which part of, but the two proofs are very similar. And then I will say at the end which part needs to be modified in a non-black box way to make it work for the general model. Okay, great. Any questions before I move on? All right. So I guess the proof, the first step of proof, I guess in most of the structural low bounds is to apply Yau's minimax lemma and say that instead of arguing for the low bound for randomized data structures, we'll design a hard distribution and then argue all deterministic data structures, the behavior of them on a hard distribution, on this distribution. And prove that the expected time must be large. And the hard distribution for this problem is actually quite simple. We just insert a set of random keys and a set of random keys, and then keep deleting one key and insert another key, and keep deleting one other random key and then insert another random key. So I guess more formally, what I mean is that I'm going to insert n random keys. And then repeat we'll first delete and I guess a random initial key. Then we're going to insert another random key, a new random key.
You insert them with random values.
Yeah, that's a good question. I'll do this n times. So I'm not really specifying the values in this hard distribution, because in the slot model, this actually doesn't matter, because all the requirements on the data structure is about the keys and also the mappings to these slots. So the values will just be stored atomically in those slots. So they are not really relevant for the lower bound or the property of the data structure, but I guess in general, for the self-prone model, we will be inserting random values. Okay, so yeah, so we just insert random keys and then keep deleting and inserting new random keys and repeat this n times. And we'd like to argue that the second phase must take n log star of n time in total. And just to make things a little bit simpler when I'm referring to this pair, I will call this a meta operation, just a pair of insertion deletions. So before I formally prove the lower bound, maybe I think it's good for me first to give some motivation about why this log star of n is the right number that we should expect. So to do this, I will actually give a very simple upper bound or algorithm against this distribution that has log star of n operation time expected with high probability. And then the lower bound, in fact, is inspired by this algorithm. Okay. Simple log star of n upper bound for this distribution. So okay, we first insert n random keys. Let's say we put them in the slots, and then maybe we keep the keys, keep the mapping so that the keys are in the sorted order, so that we don't have to store many of the auxiliary bits to say what it is. So initially, we have these n keys that are mapped in the lexicographically order, graphic order, and then at each of the rounds in the second phase, we are going to delete some key. Maybe we have a key here, and then we delete it and then insert another key. But this, as I mentioned earlier, this order it's very expensive to maintain. So I will not just always maintain this. But given that we have extra space of all of n bits, so we don't really have to maintain it at this time. So I guess one thing we could do is to just store this new element in the entry where the previous one was deleted, and also note in this using those log n bits, using logarithms out of this all of n bits, which key is out of order and where we are storing it. So this takes log n bits to describe, and I keep doing this. Maybe I have another key that was deleted later, and then I inserted another key x2 prime in it, and then I use another log n bits to do it, and so on. Do one more. But of course, I cannot keep doing this because maybe after n over log n insertion deletions, I will run out of space. Okay. Then what I can do next is that first I cannot, when I have inserted n over log n things.
N over log n.
Sorry, yeah, you're right. Sorry, yeah, n over log n things, I cannot afford to sort everything again. This is because that in the amortized sense that will be log n time per operation. But what I can do is to sort all these elements within themselves. So what this means is that we will add just a cost of 1 to each of the insertions in the amortized sense. And also the sequence becomes more sorted. Okay, so I guess more concretely, what I mean is that keep the sequence, I guess keep the mapping of the slots roughly sorted. And store the out of order elements out of order key information in the memory. I guess this will be of log n bits per key. And then we repeat this for of log n over, sorry, n over log n times. And then I'm going to sort all new keys within themselves. Okay, now how much bits do I need to describe the current state of the mapping? I need to describe what is the set of new keys among all the n keys and where they are located. But I also only need to store the set among all n locations. So this means that now we only need log of n choose n over log n bits to describe, which is let's go of this, which is of n over log n times log n bits.
This is U, no? Where you wrote n choose n over log n, isn't it U instead of n?
Isn't it what?
Log of, this is n or just
N.
n? Yeah, very good, yeah.
To describe. Yeah, we need to describe the set within the set. And this now becomes O of log n bits per key. But also I'm touching every new slot once more to solve them. And I guess after doing this, I have saved some space, freed some space, and then I can keep doing this every time I insert a new key. Maybe I replace this y with some other y prime and so on. Then I will just use log n bits on those y's. But when I run out of space on the next I guess batch of elements, I will do another sort among these new y's. So the first time I sort all these x for the first batch, and then I save space. Then I keep doing this. Then next time I have a lot of y's. When I have another n over log n new insertions, I will sort again among this batch of elements. So if I guess more formally, what I mean is that if I call this a batch of elements of keys, then after a batch, I will keep doing this, and for the I'll go to here. Now I'll just repeat now log n over log n times our batches. So for every batch, I use log n bits initially. At the end of batch, I will sort within the batch, and after batch, I'll do it again until I have that many batches. Then I will sort all batches within themselves. I guess then again, now I have n over log n elements within all those batches, and it takes like log n per bit bits per key. Which is log n bits per key. Okay, and I keep doing this. Okay, so I hope the trend is clear that I have many levels, and every level I will just do lazy updates. Whenever something happens, I just put it there, and when I run out of space, I will sort the current set of keys within the current level. When the current level is full, when I'm running out of space because the current level have too many batches, then I will sort the keys among themselves and so on. But for every level, whenever I do the sorting, I will increase my time in amortized sense by 1 per insertion. But also I reduce the cost of remembering the locations by another log. So at the end of the day, I will just be using like constant bits per key, and at the time, my time has increased to log stop n, but I can also afford to just resort everything because I have inserted things already.
Like to do their jobs.
So any questions about this? Okay, good. Okay, now, as I briefly said earlier, that the lower bound is actually inspired by this particular algorithm. Okay, so what we are going to show is that all these rounds in different channels are actually necessary. That we do have to reorganize the keys frequently, otherwise we'll be running out of space. So more formally, what I mean is, okay, so more formally, what I want to show is the following. So for we're going to look at so we first look at the first level where we initially just store the keys using log n bits, and we are going to say that for any m, which is some constant times n over log n, I guess C is a sufficiently large constant, consecutive operation. Meta operations, there must be a linear in M number of times where we access the same slot in multiple operations. There must be omega of M times that we access the same slot in I guess during multiple meta operations.
What does it mean?
Yeah, okay, yeah, what does this mean? Okay, so let's think about the algorithm. So initially we just we have those slots, and then every time we insert something, we just put it in the corresponding empty slot. But at the end of the first level, where we have accumulated enough such order elements keys, we're going to sort all those keys within themselves, which means that during that time, we are going to touch every slot that we have just inserted, and then just put those keys in order.
So multiple is 2.
Yes, in this case,
Multiple
multiple is 2.
2. So every linear in M number of cells will be touched at least twice.
Okay, so in this case, it will be 2. And in general, what I mean is that if a slot is touched in T meta operations, I'm going to count it T minus 1 times.
Yeah.
Yeah, okay, that's good. Awesome. Yeah.
Why is the upper bound algorithm specific to this distribution?
Okay, good question. Yeah, maybe. Yeah, I think it actually works in the slot model.
Worst case.
Is it true? Yeah, maybe I think maybe it's true. Yes. Yeah, that's a good point.
So does that mean the only reason why it doesn't recover that result is the computation time?
Yes, right. Because here all the things are very global. I think you have to like to solve the keys. You need to. I guess one thing is specific is that here the set of keys that are maintained implicitly in the memory. But in order to say what the keys are using in the memory, like in very small amount of time, that's not a trivial step. Like just to maintain what the keys are in the memory.
Yeah, but the distribution didn't play a role in the algorithm.
Yeah. I think that's right. Yes, I guess the upper bound doesn't just for this distribution. It works.
Yeah. You will use it here. You will use it in the lower bound.
Yes, I'll use the distribution in the lower. Yes, that's right. That's a good call. Okay. Yeah. For the first level, right? I guess I want to show that there's a linear number of times where we access the same slot during multiple meta operations. I guess equivalently saying, okay, maybe let me state the general statement. And in general, for the high levels, what I want to show is that for any m that is some constant times n over iterative log of L times, which corresponds to the level L batch in the algorithm. And this is partitioned into lambda, which is I guess log iterative log of L minus 1 of n, and divided by L iterative log of n segments of size of n over log L minus 1 n, which corresponds to the level L minus 1 batches. There must be a linear number of times where we access the same slot during multiple segments. A slot is accessed during multiple segments. So now during one segment, I may access the same slot multiple times, but I will just look at for each segment, for each slot, I will look at which segment accesses this slot at least once. And then if there are t of those segments, then I will count it for t minus 1 times. So I guess equivalently, this is equal to the number of accesses such that the previous access to the same slot was in an earlier segment. I claim that this is just equivalent to that the previous access to the same slot is in an earlier segment.
You mean just the immediately previous or some previous?
Some.
The immediate previous,
The immediate
previous
the immediate.
to the same slot. So like if I have a few I have those segments, there are lambda of them, and then I look at one slot I. Like if I access here once, maybe here multiple times, and then maybe 0 times here, but once here, then it's accessing 3 different segments, so I want to count it twice. But then, like this particular access has the immediate previous access to the same slot in an earlier segment, and it's also true for this last one, where the previous access to the same slot is in an earlier, but not for these two. So I'm just counting the first access to the within the segment that is not the first segment that passes. Does this make sense? All right. Okay. Yeah. So, for any questions about what I wanted to prove? Okay. So I will claim that this statement already implies the log star of n lower bound in the slot model, just a bit by roughly the same calculation, same way of calculating the bound for the upper bound. I guess let me just briefly say why this is true. I guess the idea is that we just look at the sequence of n operations. So this is the time. And then we have first operation, second operation, and so on. Then we're going to group the first n over log n operations into the first group. Let's call it let's say n over log n. And the next n over log n operations into the second group, n over log n, and so on. Then we're going to group the first log n over log n groups into a level 2 group, and so on. So the size of a level 2 group will be n over log n. Then keep doing this. In total, I will have log sum of n levels of this tree.
So you say this is a similar argument to these arguments with epochs that were used for dynamic.
Yeah, there's some similarity to the epoch argument, but
the numbers are different because there are no log stars there. But
yes,
yeah, you have a hierarchy or a family of scales,
yes,
and for each scale you lose one in your whatever count.
yes, yes, exactly, yes. I guess more formally, what this means is when I look at an operation here and see, an access here to a slot I will look at the last time when I access the same slot, maybe it was here. Then I will associate this access to this slot to the lowest common ancestor of these two nodes. So I look at it was accessed here. The last time it was accessed is in somewhere earlier. Now in this tree, I'm going to find the lowest common ancestor of these two nodes, and then I'm going to associate this particular access to this node. So for each access, I'm going to associate, we find the previous access, the last access to the same slot. Then associate this one to the LCA of these two nodes. Then if I look at the number of slot accesses that are associated to a fixed node in this tree, I claim that that number is basically the number I'm lower bounding here, because this is essentially, by this definition, we are lower bounding the number of accesses such that the previous access was within this node, but in a previous segment, right? So this is consistent with the fact that the LCA, the lowest common ancestor of these two accesses, is this node. Both of them are within this node, but they are in different segments. So, so without going into details, this basically means that the number of accesses associated to each node of size m will be lower bounded by linear in m. Now, every access is associated to one node at most. Then when I sum up everything over all the nodes, because every level is a partition of the n operations, so I will sum up to n log star of n. So sum number of associate accesses is at least omega of n log star of n.
You still didn't use the distribution.
Yes, that will be used in the proof here. But I guess I'm not sure if I will have time to go to the detail of the part that uses the distribution. But let me finally show why that is true. But just to demonstrate the main idea, I will focus on the first part, just to focus on the part where the first level where we have n over log n operations, and instead of segments, I will just look at the meta operations and say there will be a linear number of them that are accessed during multiple meta operations. And the intuition is basically same as why we are constantly rearranging, sorting the algorithm sorting the elements in the upper bound, because storing those like we'll be running out of space otherwise. So then okay, so let's imagine imagine that we have the memory, and then we also have these. So this is the slots, and also we have those M operations. So imagine that I give you that the memory state at the beginning of those M operations. And also I give you the memory states at the end of those memory M operations. So by definition, those two memory states should determine the initial set of keys and also the final set of keys, which determines the set of keys that are deleted in the middle and also inserted in the middle. So that is fine. But if the algorithm is such that let's say for simplicity, it does not even access any slots during multiple operations. So we're trying to prove a lower bound of omega of m, but we assume that this number is 0. Then in that case, what happens? So what will happen? So maybe the algorithm is something like every time I delete some key, and I just put the new key here, and then next time maybe I delete some key here, but I also put the new key there. Then the observation is that by comparing those two memory states and the corresponding mapping, I can actually figure out a matching between the order of deletions and the order of insertions. Like for example, if I actually do this, then for every key that was deleted, then the key that was initially inserted after that will be stored in the same location. So this means that if I tell you the deletion of order of deletions, then I can also figure out the order of insertions. But that's something that is not supposed to be stored succinctly in the data structure. That's auxiliary information. But when m is sufficiently large, like more than n over log n, this is more than log n bits of information. So I guess more formally, we prove this using a communication game. So how much time do I have?
7 minutes.
7 minutes. Okay. So yeah. Let me just briefly say what it is. So the way we prove it is to say that we have two players, Alice and Bob, where Alice initially, so it's played on these M operations such that we have the initial memory state M start, and the final memory state end, and also the initial set of keys and the final set of keys, which is k delete some set and insert some other set, and also we have the deletions and also the insertions. I call this sequence D and this sequence A. Okay, so formally what we will prove is that using a two-player communication game where the first player knows everything, Alice knows everything, and Bob knows everything except for the order of the insertions. And we will show that Alice can actually send a very short message to Bob such that Bob can actually figure out the ordering. So everything but the order of A, I guess also not the final memory state, because that implicitly depend on the order. Then we are going to show that Alice can send this final memory state using very few bits of communication. Using only O of n bits of communication. And then Bob can figure out or can recover the vector, the order using this.
This is for contradiction, right?
Yeah, this is for contradiction.
Yeah,
sorry, yes.
It's only linear memory, then.
Yes.
Yeah, that's a contradiction.
Yes.
Because
Okay.
you have some information theory.
Yes. Okay. You're right. So assume for contradiction that this number is actually very small. In fact, I guess for this talk, let's even think about the case where the number is 0, so that it's easier. So no slot is accessed in more than one step. So I guess the two will have a contradiction because the order of A is uniform random, which has too much information. And the first step is the first part is just because the final memory state must determine the final set, but Bob knows the final set. So there's only O of n bits remaining, O of n bits of information remaining. So we can show that, I guess it's not hard to show that the entropy of the final memory state is actually low. So Alice can just encode a condition on the final set. So using optimal encoding. And then for 2, let me briefly mention why this is true. So let's imagine, okay, suppose the recovery algorithm for Bob will actually try to recover those insertions one at a time. So we'll just focus on the first insertion. Consider A1. Okay, let's think about in general what the algorithm can do for the first meta operation. So you have those n slots. And then D1 is deleted here. And then we insert A1. And without loss of generality, we can always assume that the algorithm does something like first puts A1 into the empty cell, then immediately apply any permutation around those slots. So I can immediately I can put A1 in the only empty slot, then immediately apply an arbitrary permutation. So maybe this slot is moved to somewhere else, and then it's moved somewhere else, and then moved back after some steps. But any permutation is a union of cycles. I guess maybe there are some other cycles that just move things around for some reason. But the point is that if we have this assumption that no slot is accessed in more than one meta operation, that means that for anything that was accessed here must remain in the same status as in the until the end of those M operations. Which means if we look at Bob knows which slot was deleted, what is the deleted key. Then by just looking at what is stored there, if it is a new key, then Bob knows exactly this was the key A1. Otherwise, it was some earlier key, then Bob knows that in the first step, that was the key that moved to this location. Then Bob can further look at what was stored there at the end of the operations. And then it was another key that was already in there at the beginning. Then Bob knows that it was moved from other location, and then keep tracking those locations backwards using those two memory states. And eventually Bob was able to find some key that was a new inserted key, and he knows for sure that that key must be A1 because no slot is allowed to access more than one time. So and then yeah, let me not write out the details, but this allows Bob to recover A1 and then just iteratively doing this, just like once he knows A1, he's able to recover A2 using the same strategy and so on. And eventually he's able to recover everything. And in the general case where we would like to lower bound this number by linear numbering M, just the same argument applies that if they are smaller than 0.01 M, such times where the same slot is accessed during multiple operations, then the same argument just applies on the rest of the 0.99 M of the steps. So Bob is still able to recover sufficient information to get a contradiction. And for the higher levels, it's essentially the same game, except for figuring out the exact ordering. We would like to figure out what is the set that was inserted first, or in other words, which segment each insertion belongs to. And it turns out the same strategy still works. Okay, I guess, yeah, I won't have time to talk about the generalizing to the self-proven model, but that's all I want to talk about today.
Okay, thank you. Thanks. Any questions to Huacheng?
So in the slot model, you didn't need queries in the lower bound?
Yes, that's right.
And so just when you move to subgroup, somehow that there's some intuition as to why.
That's a good question. So it was, I would like to say that it's mostly for technical reasons, because I tend to think that without the bound query, we should still have the same lower bound on the update, even in the self-proven model, even when the value is small.
But you don't know how to prove it.
Yeah, but I don't know how to prove it. We tried for some time, but I didn't get that.
So what's the biggest, open problem you like in the self-proven model?
Good question. I guess something that related to this would be to prove a deterministic dictionary lower bound or upper bound. So everything I'm talking about here is randomized, and you can achieve constant time. But for deterministic, like even without space constraint, I don't know. I don't remember the best bound, but it's something like maybe square root of log or something.
The I type of bound.
The upper bound.
Oh, the upper bound. Yeah.
And there's no non-trivial lower bound.
And the square root log n is the Friedman.
Okay.
Which one is?
I don't remember. I think it's.
There's the sorting, right? So basically, you can sort in it.
I think it's a different one.
Okay.
Yeah, but I don't remember the exact bound. But I guess the question is that I think people believe in it's not possible to get constant time. So the question is that whether we can prove any super constant.
More questions? All right, thanks.